Hello everyone, this is Mahendra Varma. I'm presenting the final project of the subject data centers scale computing. The project is Distributed Rule-Based File Orchestrator, and the team members who have worked on this project are myself, Mahendra Varma, and Pranav Chopdekar. Let's move on to the problem statement. Organizations receive thousands of files every day from web portals, APIs, emails, and automations. Manually sorting or reviewing these files is slow, error prone, and does not scale. AI based classifiers are often expensive, inconsistent for enterprise workflows. They can also be very unreliable and unpredictable. So we designed a system that uses deterministic rules to reliably organize files across the clouds. Our goals were to build a reliable, high throughput pipeline capable of processing 5,000 plus files per hour, achieving 99.9% availability, and automatically scaling based on system load. We also wanted cost efficient through lifecycle policies, deep observability using BigQuery and cloud monitoring, and an architecture that demonstrates real data center scale distributed system design. This is the high level architecture. User uploads file through an API. Files are stored in cloud storage, which triggers a sequence of worker through pub/sub events. Inspect, classify, and act. Each worker runs on Cloud Run for automatic scaling. We track job status in Firestore and store analytics in BigQuery. This modular event-driven architecture lets each stage scale independently, making the system resilient and highly efficient. Sorry. Cloud and software components. Our system uses several GCP services, cloud storage for multi-bucket design, pub/sub topics for each pipeline stage, Cloud Run for autoscaling, BigQuery for analytics, Firestore for tracking rules, job status, and Secret Manager for secure credentials. Our development stack includes Python, FastAPI, Docker, YAML-based rules, and Redis caching. Supporting infrastructure includes container registry for images, cloud load balancer for routing, VPC networking, and optional cloud functions. Our architecture runs on four-stage pipeline. The ingest stage receives file and publishes the job. Inspect stage extracts metadata. Classify stage applies YAML rules. And finally, the act stage moves and labels the file. This clean event-driven sequence allows horizontal scaling and clear separation of responsibilities. The ingest stage. This stage begins with our fast API upload endpoint. We validate the file, generate a job ID, store the file in cloud storage, and publish a message to ingest pub subtopic. We also mark job as pending in Firestore, enabling complete traceability throughout the pipeline. The next stage is the inspect stage. Inspect stage worker reads the file initial bytes to extract the magic signature and the true MIME type. We pass metadata such as EXIF data for images, PDF, and Office document properties, and compute a SHA-256 hash for deduplication. We also run regex-based checks for things like invoice numbers, dates, financial amounts, and the file name. Inspection results are saved to BigQuery and Enriched metadata is published to the classify topic. The job is then marked as inspected. In classify stage, we load the YAML rule configuration from Firestore and apply deterministic matching logic. Rules can match on MIME type, file extension, keywords, EXI of data, and any inspection metadata. Once rule matches, the classification result is published to the ACT topic and the job is marked classified. The ACT worker performs final operation on the file. It moves a file into correct organized folder, applies metadata labels such as retention or archival policies, and writes final metadata into BigQuery. After the action completes, the job is marked completed in Firestore. For debugging, we relied on structured JSON logging across Cloud Run, PubSub retry logs, and Firestore job tracing. BigQuery inspection logs helped us validate metadata extraction and performance. For testing, we created unit test cases for all workers using PyTest and simulated PubSub push requests locally. We performed end-to-end tests by uploading files and verifying they flowed through all four stages. Now let me give a demo of this system. We upload, so you can see the UI of this system. There are three main components in the UI. First component is to upload a file, and the next component is the rules section. User can create his or her own custom rules. And on the right hand side in the rules section, you can see the existing rules. And the final section is the recent activity section. This shows all the recent activity or all the activity that has happened in the system. Let me upload a file. The file is named info 46025602 paper 7 summary final PDF. As you can see, there is an existing rule. So this rule moves all the files which has the name that contains info 4602. These files are moved into the InfoVis directory. So this is one custom rule, but there are already few inbuilt rules that classify the files based on MIME type or extension. That is, PDFs are moved to PDF folder, text files are moved to text folder, and images are moved to images folder. So I have uploaded this file, and you can see in the recent activity, a new entry has been added that shows the action moved to InfoVis directory. Now let me upload another file. Uh, I am uploading a text file that is sample.txt. So after uploading this file, you can see a new entry that says the action as moved to text. So the file that I've uploaded, sample.txt, is moved to a text directory within the cloud storage bucket. Now let me show you the Firestore database. So as you can see, there are four entries here. So these are within these entries, you can see the different stages like action, classification, inspect, and source. In action, you can see the destination bucket and destination folder. And in classification, it shows the classification type and the MIME type. Let me show you the storage buckets. So here are the storage buckets. DRBFO uploads holds the initial uploaded files. Later, later on, a rule is matched for the file that is uploaded into this bucket, and according to the rule, the file would be moved to the DRBFO organized bucket into different directories. Here you can see Infobus directory, PDF directory, and text directory. PDFs hold all the PDF file, and text directory holds all the text files, and Infobus directory holds all the files that are matched to the custom rule Infobus. And capabilities and limitations. Our system is fully automated, rule-based, and horizontally scalable. It provides excellent observability, predictable behavior, and low operation cost thanks to serverless components. However, Cloud Run cold start can add latency, large file take longer to inspect, and complex rule sets increase processing time. Like any cloud native system, it also depends on the availability of underlying GCP services. I forgot to mention one thing within this cloud file orchestrator. So in case there are multiple rules that are applying to the same file, the rule is chosen with the priority section. So the rule that has higher priority is chosen and the action according to that particular rule is applied. In future, we plan to develop a real-time dashboard, support multi-bucket and multi-tenant workflows, and introduce rule caching to reduce latency. We also want to support parallel batch processing and integrate more advanced metadata extraction modules. To conclude, the distributed rule-based file orchestrator demonstrates production-grade serverless event-driven pipeline for organizing files at scale. It is deterministic, highly observable, cost-efficient, and designed using modern cloud architecture principles. Thank you.